Okay, today we're going to talk about how to make a prediction about a population proportion if we have a sample from that population. The first thing we have is an estimate of our proportion, and we call that our point estimate. And we only have the information we gather to go by, and so we take the number of our positive outcomes that we're looking at over our sample size, and that's how we get our point estimate. And that goes in the middle of our confidence interval. 1 minus alpha equals our confidence level. And our confidence level is the boundaries around our confidence interval. So if we wanted to have a 90% confidence interval, then 1 minus alpha would equal 0.9, which would mean that alpha is 0.1. To find our z values for a 90% confidence interval, then we use z alpha over 2, and that's going to give us the z values around our confidence interval. So if we want a 90% confidence level, we have z 0.1 over 2, which is the z value that goes with 0.05. To find that, you do inverse norm of 0.05. And the z values that go with that are plus or minus 1.645. In this case, if our confidence interval is 0.9, then it makes sense that we have 10% left over, and we put 5% at each end. So z is positive 1.645 over here. For a 95% confidence level, that means that our alpha, if 1 minus alpha is 0.95, then alpha is 0.05, which means that z alpha over 2 is going to be z 0.05 divided in half, which is z 0.025. So our point estimate goes in the middle. The z value, by the way, for that is 0. .95 would be the range in the middle, and on each end we would have 0.025. And the z-scores that bound that we would find using inverse norm again, 0.025, which is going to be close to 2, but not quite. It's negative 1.96, and over here z is positive 1.96. And the last common confidence interval that we might want to find would be a 99% confidence level. In this case, alpha is 0.01, and z 0.01 over 2 is z.005. And to find that inverse norm of 0.005 gives me plus or minus 2.58. Again, p hat would be in the middle. Z equal to negative 2.58 would be my lower bound. And z equal to positive 2.58 is the z value that goes in my upper boundary. So we set up our confidence intervals based upon how accurate we need to be. Some of the things that might require a greater accuracy, like a 99% confidence interval, might be if you were a drug manufacturer and you were, or drug researcher, and you were testing drugs on people. You'd have to be pretty accurate for that. There's a couple of conditions required in order to have a valid large sample confidence interval for proportion. First of all, our sample needs to be random and it has to be from the target population. The second thing is that our sampling distribution of our estimated proportion, or p hat, that's p hat, is approximately normal, and it has to satisfy the following condition. It has n times p hat times q hat has to be greater than or equal to 10. So p here, that is the population proportion. That's the true population proportion that we don't really know, but we're guessing at. And p hat, that's what we observe. That's the number of successes over our sample size. That's our best estimate of what we think the proportion is. We call it a point estimate. And the formula for finding our boundaries around our point estimate, our lower boundary and our upper boundary of our interval, is going to be p hat plus or minus z alpha over 2 times, this here is the standard error. It's p hat times q hat over our sample size. When we do it in an example, it's going to make more sense. Okay, looks like I have the wrong slide in here. You're going to have to follow along with your notes. I'll read it, but you're going to need to follow along. A Rasmussen report, national survey of 1,000 adult Americans. So we have 1,000 adults, and that's equal to our sample size. Found that 18% dreaded Valentine's Day. So our point estimate is 18%. Is the sampling distribution approximately normal? If so, construct a 99% confidence interval. So we have to test out whether this is valid or not. And to do that, n point estimate and q hat need to be greater than or equal to 10. So let's test that out. We have 0.18 times 0.82 times 1,000. And when I calculate that, I get a value of 147.6, greater than 10. So this will be a valid large sample confidence interval. All right, so we want to calculate a 99% confidence interval. That means that 1 minus alpha is equal to 0.99, our confidence interval. That means that alpha is 0.01, which means that z alpha over 2, we've calculated that already, for a 99% confidence interval is going to be plus or minus 2.58. If you need to see how that's calculated again, go back to the beginning of the video. While we're at it, we may as well calculate our standard error. That's going to be p hat q hat over our sample size, which is going to be 0.18, oh, the square root of that, 0.18 times 0.82 over 1,000, and then take the square root of that. I get about 0.0122. Now we have all the values to set up our boundaries. Let's take a look at our confidence interval, or a visual of it. So in the middle is our point estimate, and our point estimate is 0.18. We want the values that bound that. So our lower boundary is going to be our point estimate minus z alpha over 2 times our standard error. And we've already got all of those values figured out. So that's going to be 0.18 minus 2.58 times 0.0122. When I calculate my lower boundary, I get 0.1487. Now for my upper boundary. Oh, by the way, that value goes up here, 0.1487. It's our point estimate plus z alpha over 2 times p hat q hat over n. So it's going to be 0.18 plus 2.58 times 0.0122. And calculating that, I get 0.2113. So that is my upper boundary. If I ask you for a confidence interval, you're going to give me in interval notation, that's what this means. You're going to give me the lower boundary first, and then you give me the upper boundary second, with a comma between them and parentheses. If I asked you to construct or to construct the confidence interval, you could say that the number of Americans who dread Valentine's Day is 18%. Plus or minus 1.49%. Actually, 1.22. Whoa, where did that come from? Percent. with 95% confidence, or 99% confidence. Okay, so I can't add or subtract. It's actually plus or minus 3.13%. How do I get that? Well, it's the difference between the point estimate and either the top or the bottom boundary. All right, let's try another example. All right, in a USA Today Gallup poll, 768 of 1,024 randomly selected adults stated that a candidate's position on the issue of family values is extremely or very important in determining their votes for president. First of all, what's the point estimate? That'll be easy. The point estimate is the number of values we observe over the sample size. So 768 over 1,024 gives me a point estimate of 0.75. Find a 95% confidence interval for the proportion of adults for which family values are important. All right, we want a 95% confidence level. That means that alpha is 0.05 and z alpha over 2 is 0.025. And from our values earlier, we know that's plus or minus 1.96. Remember, 95% confidence interval, 99% confidence interval, and 90% confidence interval are values you might want to remember or try to memorize because we use those the most, especially this one. This is probably the most common one. The other thing we're going to want to find is the standard error. Since our point estimate is 0.75, then Q hat is going to be 0.25, and our sample size is 1,024. When we take the square root of all of that, I get 0.0135. Hopefully that's what you get to. So if we look at what that looks like, point estimate in the middle of 0.75, looking for the values above and below 0.75. We're going to find those using the number of standard errors away from the mean we are, or from our proportion we are. So we have 95% in the middle and 0.025 on each end. So our lower boundary of our confidence interval, the lowest boundary we think that the proportion of population is 0.75 minus 1.96 times 0.0135. And when I calculate that lower boundary, I get 0.7235. So this would be 0.7235. So I think that the lower boundary would be 72.35% who think that family values are very important. And then the upper boundary will be 0.75 plus 1.96 times 0.0135. And for that, I get 0.7765. So I think that the true population proportion is somewhere between 72.35% and 77.65%. The confidence interval then is 0.7235, comma 0.7765. If I want to make a statement about that, I'm going to say the proportion of adults who think family values are extremely or very or extremely important is 75%, plus or minus 2.65%, with 95% confidence. It's important that you learn how to write a confidence statement as well as find the interval. Okay, here's one for you to try. Pause this, and when you're ready to check your answer, turn it back on, and we'll check your answer. Okay, I'm just relieved I have the right slide on here this time. Okay, a Harris Interactive poll conducted in the U.S. in January 2008 found that 322 of the 2,302 adults aged 18 or older have at least one tattoo. I'll bet that's changed now. Anyways, construct a 90% confidence interval. What is the effect of increasing the level of confidence on the width of the interval? All right, so let's find our point estimate because we can't do anything without that. That's our number of observed over the sample size. And that I calculate to be 0.1399. So that's going to go in the middle of our point estimate. 1 minus alpha is 0.9, since 90% is our confidence interval, which leaves 10% on each end. So alpha is 0.1, and if we divide that by 2 to put half of it on each end, and we're looking for z 0.05. And that we have calculated earlier for a 90% confidence interval to be plus or minus 1.645. Standard error is going to be p hat q hat over n (1399). Why can't these numbers be nice? 0.8601 over 2302. I calculate 0.0072. Hopefully you do too. All right, upper boundary. Oh, let's find the lower boundary first. I like to do things in order. So our point estimate is 0.1399 minus 1.645 times 0.0072 gives me 0.1517. Nope, just kidding. That's my upper one. actually gives me 0.1281. And when I add that value, I get the other one instead. That's when I get 0.1517. All right, so my confidence, the interval is 0.1281 to 0.1517. That's my confidence interval. My statement would be the percentage of adults who have at least one tattoo is 13.99% plus or okay. Let's see what happens when we know the point estimate. Now assume we have an estimate which suggests that 34% of college students have $2,000 or more of debt. So our point estimate is 0.34. At a 99% level of confidence, that means that z alpha over 2 is z.005, and we know that is plus or minus 2.58. Find the necessary sample size if the sample is to be within 2.5 percentage points. So the error that we are willing to accept is 0.025. All right, so our formula for sample size is z alpha over 2 squared divided by our error squared times p hat times q hat, which means we need q hat. And q hat is 1 minus 0.34, so it's 0.66. Plugging in our values, we get 2.58 squared over 0.025 squared times 0.34 times 0.66. Putting all of that into a calculator, but be careful about your order of operations, and I get 2389.9. Always, always, always round up. Even if you have the teeniest bit of decimal, you need to round up. And your sample size needs to be 2,390. All right, that's it for tonight.